Everybody, welcome back to another episode of Yo at Home. Hope you're doing well today. So, in the physics of waves, we have a variety of terms, and we want to make sure we understand the terms thoroughly. The first term that we have is dispersion. Dispersion is that the speed of a wave depends on the wavelength of that wave. So, some examples of that. Any medium where light passes through is considered to be a dispersive medium. Other than a vacuum, where all waves would travel at the same speed, any other medium, the wave speed depends on the wavelength. So, let's look at a prism. Prism is an excellent example of this. When white light hits a prism, it's dispersed into a rainbow of colors. The reason we see a rainbow is that the different wavelengths travel at different speeds and are bent, refracted, at different amounts. So blue light you see is bent the most, red light is bent the least. Blue light is slowed down the most. The way we can think of that, it is not exactly true, but you can think of it as blue light is vibrating with a shorter wavelength, so it interacts more with the medium, and therefore it is affected more by it. Red light, with a longer wavelength, really is not taking as long a course through the medium, so it's affected less. And you can see the wavelengths bent like that. Well, the question might arise, does dispersion happen with sound as well? And I could tell you, yes, dispersion happens with sound as well. Now in air, does air disperse sound? Well, think of your hearing of a distant object. Do you catch one wavelength first and then the other wavelength? I think you'll recognize the answer is no. However, in other media, sound is dispersed very, very well. You may have heard this sound. That's the sound of a slinky being hit. Well, why does it sound so odd? What frequencies are getting to you first? Well, clearly if you listen to it again, the high frequencies, in this case, get to you first. They're moving very quickly through this medium. The low frequencies get to you next. That's why you have that incredibly bizarre sound. Isn't that cool? And that's all dispersion of sound. So both light and sound both disperse. The next thing we have is diffraction. Now, diffraction is the bending of waves around an obstacle. And when we have waves approach an obstacle, right here, right at this point here, the waves act as a new source. And if you think about if they were water waves, and this was a pier, and this is or a breakwater, and right between them, this wave hitting would simply raise and lower the water there, and it would generate new waves, and they would diffract tremendously well. So here we have diffraction of waves. And when the obstacle is small, or the opening is smaller, you diffract better. When the opening is larger, you can see diffraction will not happen quite as much. The opening, in any case, has to be similar in size to the waves that are going through it. But if it is similar in size, the smaller opening diffracts better. And the longer the waves, the easier the diffraction is to occur. So you have dispersion and diffraction. They sound similar, utterly different things, right? Dispersion is the speed of the wave depends on the wavelength. Diffraction is simply the bending of waves around an obstacle. Okay? The next thing to talk about is reflection. And reflection is simply the bouncing of waves off an obstacle. And when we have something like that occur, here is simply the law of reflection. Angle in equals angle out. Remember, all angles must be measured with respect to the normal. reflection has to be talked about with purely respect to the normal. So here you have a light wave coming in and it bounces off. Would this happen with sound waves? Have you ever heard an echo? Of course. Happens with sound or light waves. So angle in equals angle out. And that would be reflection. Simple bouncing of waves off an obstacle. Next one is refraction. Refraction is the bending of waves when they change speed. So take a look at this. And this is the Jeep story. So in this case, you have a Jeep on pavement and it wanders off until the right tire is on mud. Well, which tire is going to go faster? Just ask yourself that. Certainly the tire on the pavement. So the tire on the pavement will cause the Jeep to rotate this way. So again, all angles are measured with respect to the normal. Here's the angle in. Here's the angle out, or the angle of refraction. You can see this angle and this angle. Compare them. So if this refracts into a more optically dense medium, it's going to bend closer toward the normal. So it will decrease the angle. And of course, we're measuring it with the normal. So pavement into mud. Now, this is a common source of errors for drivers. They will drift off and hit the mud, and they will either get pulled quickly into the mud, or more likely, they will correct so they're going straight, not realizing that their tires have to already be turned like that just to keep going straight. And then when they try to pull back onto the road, they will overcorrect and move into oncoming traffic very quickly. This is a dangerous thing to do. The next thing is very interesting here with this, and this is if you're driving in the mud. All right, if you're driving in a highway made of mud and on either side is pavement, I recognize this is an unusual circumstance, but bear with me. If on either side of you is pavement, you're going to have an interesting time, because as you move from the mud to the pavement, this tire, as soon as it's on the pavement, goes faster, and it tends to keep you from getting into the pavement, tends to keep you in the mud. So the angle of incidence here is less than the angle of refraction. You are actually refracting away from the normal. So in either of these directions, you will be tending towards staying in the mud. Well, I drew it like this specifically because we use this in an interesting way. This is a fiber optic cable. This tiny little cable can carry light inside it, and it does it in this way. The core of it is more optically dense, surrounded by less optically dense media. And when I shine a laser at this, you notice the laser comes out the tip of it. And yet, when you look at the cable itself, when I'm shining a laser at it, you can see a little light at the tip of it, but you cannot see any light at all inside or coming from inside the cable, because this keeps everything inside. And it does that by what we would call exceeding the critical angle. The critical angle would be the angle here that causes this angle, the angle of refraction, to be 90 degrees. So you can see if I widen this angle a little bit, the angle of incidence, sooner or later I'm going to get to a place where I'm refracting at 90 degrees. If I go larger than that, now I don't refract at all. I have complete total internal reflection, and all the light would stay then in the mud. And that's what's happening with a fiber optic cable. So we have refraction, okay, and we use Snell's law for that. I've already taught a lesson on Snell's law. I'd refer you to again, and taught a lesson on critical angle as well. So interference then. We have two kinds of interference: constructive interference. Interference, or constructive and destructive interference. Interference is the momentary combining of waves when they're passing through each other. So let's take a look at constructive interference. We have two pulses coming down towards each other. When they meet, we have them superposition. This is termed superposition. And the superposition of these two pulses, you're simply adding the amplitude. So that's the amplitude of A, that's the amplitude of B. This is the amplitude combined, amplitude of A plus amplitude of B. Interestingly, after they combine, they continue on their merry ways, unaffected by the fact that momentarily they were part of a much larger wave. So this is constructive interference because they're adding together to make a larger wave, but afterwards they just continue on. B is unaffected, A is unaffected. Destructive interference then would be if you have two waves out of phase with each other. A in the upward direction, B in the downward direction. When they combine, yeah, that's it. That's their combination. There's no disturbance on this water at all, if these were water waves, at all. It's perfectly flat. And then a moment later, B emerges from that unchanged and continues in the direction it was originally traveling. A also emerges unchanged and continues the direction it was originally traveling. So that's both constructive and destructive interference. Okay, and interference will happen with both light and sound. So far, all of these happen with both light and sound. We see dispersion with light and sound, diffraction, bending of waves around an obstacle. If you can hear me from the hallway, must be diffraction, and diffraction certainly occurs with light as well. Reflection and refraction both occur with both sound and light. Interference, sound and light. Let's look at polarization. Polarization is something that only allows waves vibrating in one particular direction to pass. Here's a diagram of what I mean by that. So here we have the original light source coming in from here, and think of an atom. Think of a hot atom emitting light. Well, it's a group of hot atoms. Some are vibrating this way, some are vibrating this way, some are vibrating every possible vibrational direction. So every possible different direction of waves is coming off of them. So these waves are vibrating in every different direction. If we were to have, say, a super tiny picket fence, so tiny that a wavelength of light is about the size of the picket fence, and we have this picket fence up and down, we are only going to let light vibrating up and down come through that. One direction of vibration is all we would get. So we go from many directions of vibration to only one direction of vibration. Now, importantly, it's to understand if you have something that has a component of it vibrating in the up and down, then that component will go through that as well. So it doesn't have to be light perfectly up and down. Any wave that has a component of it, that'll be taken through too. So what can you do with polarization? Well, one of the more magical things that you'll ever see are two polarizing filters. If you've never met polarization before, two polarizing filters, when you cross them, now you have the two crossed picket fences, and no light progresses through them. And cross them again, you could see it. But when you do this, you have now blocked light from passing through it. Now, you can mess with this in a variety of ways. You can use this to reduce glare off your car windshield, or your car hood, rather. Because light, low-angle grazing light, hitting your car hood goes up to your windshield. But when it goes up to your windshield, all the polarizing that was side to side, all the light that was vibrating that way, goes up. All the light that was vibrating straight up and down, most of that tends to get absorbed. So if you have sunglasses that only let light vibrating up and down in, you reduce the glare coming from that, and you're able to see much better, because the light hitting this, the glary light from reflections around you, is going to side. None of that would get admitted to your eyes then. So that would be polarization. Can you polarize sound? It's a good question. Is sound vibrating in all possible directions? Well, no. Sound is a pressure wave. Molecules are vibrating by going to and away from. So if a sound wave is going this way, the molecules of the air, they're alternatingly pushed forward and then backwards. forward and then backwards. There's nothing there to polarize. You could never polarize sound. So polarization is the one thing here that is light only. And by light only, of course, I mean all electromagnetic radiation, polarizable. But sound, never. You cannot even theoretically polarize sound. So that's a few things about the waves and things we need to remember. The regents will often ask you, how would you be able to tell sound waves from light waves? And one of the answers that is very popular is that light waves could be polarized, sound could never be polarized, some aspect of something like that. But these are the major words that go with the neat things that happen with waves. Thanks for tuning in.